So the next speaker is Yahan Lee from Tianjin Normal University. Unfortunately, he cannot join us live now, but he spent quite some time preparing for his talk and he has pre-recorded it. So what I'm going to do is I'm going to play the recording he shared with us. And at the end of the recording, you will see that he already put some information on how you can reach out to him for questions about the topic he's going to present during his talk. And also if you want to, for example, check his papers and the code. So this talk is titled Federated Weakly Supervised Video Anomaly Detection from Yang-Han Lee, and I will play the video now.
Hello, everyone. First of all, thanks for the invitation and for the opportunity to share our work at the Flower monthly event. Due to some reasons, I'm presenting this talk in a pre-recorded video. If you have any questions, please feel free to contact me using the information provided on the last page of the slides. Okay, let's start. Our research focuses on Federated weakly supervised video anomaly detection, a novel application of federated learning in real-world environments. In this presentation, I will walk you through how federated learning enables effective multi-scene video anomaly detection while ensuring data privacy. So let's dive in. Okay. My name is Jiahang Li. I'm currently an undergraduate at Tianjin Normal University, supervised by Professor Yong Su. My research interests include video anomaly detection, weakly supervised learning, and real-world applications of federated learning. Okay. Video anomaly detection, or VAD, is about automatically finding unusual or abnormal events in video surveillance data. It plays a key role in improving safety and security for modern industries and smart cities. And here are some example datasets used for VD tasks. This datasets predefine a set of abnormal events, such as driving a car on the sidewalk, stealing bike, and fighting, and other abnormal behaviors. If any frame contains one of these events, we consider that this frame to be anomalous. For VD tasks, we usually use a pre-trained feature extractor to extract video features as snippets, and this features along with video labels as inputs, and are used to train the model during inference. The model can detect normal events as 0 and abnormal events as 1. There are four main types of VD tasks. First, fully supervised VD use frame level labels during training, and one class VD training only on normal videos with no anomalies in the training set. And weakly supervised VD uses video level labels. If a video contains at least one abnormal frame, the entry video is labeled as anomalous. This is the unsupervised VD. The unsupervised VD does not use any label for training. To balance the performance and the labeling cost, our research focuses on weakly supervised VD. The first challenge relates to weakly supervised learning. In fact, weakly supervised VD can be viewed as a multiple instance learning problem. This is because during training, an abnormal video contains both normal and abnormal snippets. Sometimes even within the abnormal snippets, there may be both normal and abnormal events. Since multiple people in same frame maybe doing different things. This complexity makes the problem even more challenging. To address this, previous methods typically use two types of loss function. A top K cross entropy loss for abnormal video and a central and a center loss for normal videos. In this approach, abnormal videos are treated as positive bytes, while normal videos are treated as negative bytes. The top K highest scoring snippets in positive next are selected for the cross entropy loss, while all snippets in negative bytes are used for center loss. This helps the model learn to better distinguish between normal and abnormal behaviors. However, this approach mainly focuses on the top ranked discrete snippets during training. While it is effective at identifying the most obvious abnormal snippets, it still has two main limitations. It may mistaken select the noise normal snippets as anomalous. It overlooks the lower ranked snippets that may still contain important abnormal events. You can say this two examples. Like this one. Next one. This is a normal snippet, but the previous method build this one as a select this noise normal snippets as anomalous, and this one is abnormal snippets, but the previous method overlook this snippets. These limitations can lead to cumulative misclassification of normal snippets and missed distinction of significant anomalies during training, resulting in a higher false alarm rate. And to address this problem, we designed adaptive dynamic recursive mapping. Our approach re-optimizes the score of all snippets, not just the top ones, as shown in this two example. With our recursive mapping, this low scoring abnormal snippets can get higher scores, like this. While the high scoring normal snippets can be adjusted lower, like this. So our method improve our overall detection accuracy. And the second challenge is privacy and making 3D work across many different real-world environments. Currently, most weekly supervised video and reaction models use the one-size-fits-all approach. They train a single model to handle many different diverse things, but in reality, surveillance data is managed by different organizations, and the privacy rules make it difficult to share data between them. This is not only limits our ability to build truly general models, but also reduce how well these models perform in real application. Another challenge is that the definition of an anomaly can vary from scene to scene. For example, riding a bike may be normal on the road, but forbidden in some part of the school. Training a centralized one-size-fits-all model can lead to level inconsistency for similar activities in different environments. All of these challenges make it hard to develop robust and practical models for real-world use. To address this, we introduce an adaptive local model regression algorithm. Federated learning is a great fit for VD problem because it solves both privacy concerns and the challenge of label heterogeneity across scenes. The last challenge is that most general VD methods are context agnostic. Training private weakly supervised VD method and model across multiple screens is not easy. Currently, most weakly supervised VD method are context agnostic. Like this example, they use a task agnostic pre-trained facial structures, usually trained on action recognition dataset to extract feature from video snippets and learn on anomaly ranking model. However, using these pre-trained backbones for different things can introduce domain gaps. And action recognition datasets typically contain only one person per video, while video often involve multiple people and more complex events. Some events in video may actually be combinations of several actions that make feature representation less accuracy. And real-world surveillance video are highly diverse. They have different the different things can vary in structure, lighting, resolution, and frame rate. So the context agnostic method reduce the model robustness and often miss the subtle anomalies. If local models are not well trained due to scene heterogeneity, their errors can negatively impact the aggregated global model and even propagate through the entire network. To address this, we introduce a scene similarity selection method by aggregating my models only from similar scenes. We reduce the feature heterogeneity between scenes and limit the spread of errors across the network. As you can see in this framework, we first use a pre-trained video MAD backbone to extract features from the video. The original feature has 1,408 channels. To improve computational efficiency, we compress this feature in two ways. First, we calculate the average across all channels. Second, we compute the max average and the standard deviation across the channels. These two types of features are often used as an inputs for two different detectors in our model. The channel average, the anomaly detector, outputs a decision parameter R and a CAAD score. The channel statistical anomaly detector outputs a detection parameter beta and a CSAD score. To solve the discrete optimization problem, we design a novel mapping function. the input given a score and a decision parameter. This function maps the input to a refined output score. You can see the visualization of this finger. Uh, the x-axis is the input score, and the y-axis is the output score, and the different lines represent different values of the decision parameter. For example, if the input score is this, and the decision parameter lines are is this, so we can get the output score be lower. Could be this. So we can use this function to re-optimize the anomaly score, and then first we apply this mapping to the dual detector scores using the detection parameter alpha. Because alpha comes from the averaged feature, it helps reduce sensitivity to feature noise and improve the robustness of the model. Next, we use the detection parameter beta to map the value from the statistical feature, which capture temporal correlations between video snippets, and refine the detection boundaries for smoother transitions. Finally, the outputs of both detectors are multiplied together to produce the final anomaly score. The core idea of seeing similarity adaptation local aggregation is to consider both the local model and the global model, allowing each client to adaptively update its private model weights based on its own data distribution. To achieve this, we introduced two adaptive weights measures to balance the contribution of the local and global models. We also propose selective aggregations method that aggregates clean models based on similarity. Like each client first train its local model, then based on the SSIM scores between things, each client selects the k most similar models from other clients. These selected models are aggregated from a personalized global model, which is then returned to the selected clients. To support adaptive local aggregation, we treat the aggregation process as an optimization problem. The goal to minimize the local loss function, which takes as an input local model, global model, and local data. Here, the global model weights and local data are fixed. The only variable parameters are two adaptive metrics donated as A and W, which are used to update the local model weights in that step. For a local model configuration leads to a lower loss, we consider it be a better fit for that specific link. So we use gradient descent to minimize the loss and update A and W accordingly. To ensure convergence, we monitor the last 5 loss values when the standard deviation of these values falls below 0.1, which stops the optimization. By doing this, we can train a personalized and context-dependent local model for each client in the waiting task. All right. Now let's take a look at our experimental setup and the results. We use two multi-scene datasets, Shanghai and UV This datasets help us to simulate real-world environments where each scene is treated as a separate client. For our experiments, we deploy each device in Vida Johnson AGX area as the client. We use the flower framework to manage federated learning across these devices to evaluate the performance. We use the AUC, ROC as the main metrics, and also measure the force alarm rate to check how robust our model is. We can say from the results on Shanghai Tech and Normal that our model outperforms the baseline models. It achieves higher detection performance and lower false alarm rate. Here are some visualizations of our anomaly scores on simple videos. The blue lines shows the score from our model, and the green lines shows the baseline results. As you can see, our model produces robust results for both abnormal videos and the normal videos. Here are some interesting experimental setups. In first table, we evaluate the effectiveness of each component of our framework on Shanghai. You can see that when we use all components together with SSLA algorithm, we achieve the best performance. In contrast, if we only use the fade average, the performance is lower. This is fade average performance. The second table shows cross data set evaluation. We use the Pad2 and Avenue, which are single scene data sets with different type of anomalous resolutions and frame rates. Each data set is deployed on a separate client. Our SSLA algorithm achieves the best performance and the lost false alarm rate compared with the other method. In the final table, we test the framework's ability to handle label heterogeneity. We define the riding bicycle events as normal in scene 4, 6, 10, 11, and 12 of the Shanghai dataset, while keeping the other scene unchanged. We compare the baseline centralized model and our model. The first row shows the original result. The second row shows the result with the redefined labels. And the last row shows the change in AOC scores. We can say that our method effectively handles label heterogeneity and can adopt to scene-specific anomalous definition. Besides performance, inference efficiency is also important for real-world VAD applications, especially on each device with limited computational resource. We evaluate both the facial instruction time and the model inference time during the inference phase. We found the facial instructions is the main limitation factor for real-time performance. To address this, we apply the pruning and quantization to video memory V2 model. Then we evaluated both speed and the accuracy with a polling rate of 30%. We were able to speed up the model significantly while still maintaining high accuracy. And thanks for your attention. If you have any questions, you can reach out to me by email or on LinkedIn. For more details, please check out our paper or the code. Thanks again for the attention, and see you next time.
Yeah, I think this was a super interesting work. It's the first time I see this type of work in the context of FL, where seeing similarity is a very big challenge. I think also one of the things I really like was that it's actually running on edge devices like NVIDIA Jetsons, and the results look pretty strong, especially when using the proposed SSALA strategy. So be sure to reach out to Yahan Lee for more details if you are curious about this type of work, and also check the paper on the repo. I saw his repo a while ago and I was really impressed about it.